Modern enterprise infrastructure relies on real-time stream processing. When millions of telemetry events, financial transactions, and operational metrics need to move from origin to destination, organizations route that data through Apache Kafka. This diagram shows the baseline architecture of a standard Kafka cluster. On the left, we have producers, the applications generating the data. They push raw data blocks into a central array of brokers, which store and organize the information. Finally, consumer groups on the right pull that data for processing and analysis. But as the network expands and these pathways turn red, a structural paradox emerges. Kafka is natively designed for maximum throughput and low latency. Out of the box, it prioritizes speed over security, leaving these communication lines wide open. Operating a cluster in plaintext creates an enormous attack surface. Anyone with access to the network can eavesdrop on sensitive data in transit. Bad actors can tamper with the data payloads or spin up unauthorized rogue consumers to quietly drain your internal data feeds. In partnership with Royal Research, we are going to break down how to harden this infrastructure. Securing a deployment requires implementing a strict three-pillar architecture: authentication, authorization, and data protection. Deploying Kafka without these three pillars in a production environment exposes the nervous system of an enterprise to severe risk. The engineering objective must shift from maintaining raw speed to ensuring secure, verifiable transit. The most immediate vulnerability is the data moving through the network. When communication between clients and brokers is completely open, attackers can execute man-in-the-middle attacks, intercepting and reading sensitive streams in plaintext. Looking back at the diagram, we solve this by wrapping those vulnerable pathways in opaque conduits. This represents the implementation of Secure Sockets Layer, or SSL, and its successor, Transport Layer Security. TLS encrypts the data in transit, making the streams unreadable to anyone intercepting the traffic. Implementing this requires precise cryptographic management. Every single broker and client in the cluster must be equipped with a key store, which holds its private key and unique certificate, and a trust store, which contains the certificates of trusted certificate authorities. When a connection is initiated, the broker and client use the keys within these stores to perform a cryptographic handshake. They verify the digital signatures and establish a secure encrypted session before a single byte of data is transmitted. For environments requiring zero trust security, administrators can configure an advanced setting known as Mutual TLS, or MTLS. In a standard TLS setup, only the server proves its identity to the client. Mutual TLS forces bidirectional verification. The Kafka broker demands a valid certificate from the client application, and the client demands the same from the broker. TLS secures the transport layer. It hides the data and verifies that the machines talking to each other are recognized by the certificate authority. However, it provides zero visibility into the application layer. It confirms the device is trusted, but it does not tell the cluster which specific user or application is actually operating that device. A common operational mistake is assuming that SSL encryption provides complete authentication for a cluster. This side-by-side comparative stack illustrates the gap. SSL and TLS operate down at layer 4, the transport layer. They secure the pipe. To verify the actual identity of the user inside that pipe, we need a framework operating at layer 7, the application layer. Kafka relies on the simple authentication and security layer, or SASL, to solve this identity problem. SASL is a framework that allows Kafka to plug in various connection-based user authentication methods. The most basic authentication mechanism is SASL/plain. This requires the client application to submit a standard username and password to the broker for verification. Because SASL/plain transmits credentials in clear text, it is completely unviable for enterprise use on its own. It must be deployed strictly inside an existing SSL or TLS encrypted tunnel to protect those credentials from exposure. For internal authentication that doesn't rely entirely on the transport layer to protect passwords, administrators implement SASL/SCRAM. SCRAM stands for Salted Challenge Response Authentication Mechanism. Instead of sending a password over the network, the client and broker exchange cryptographic proofs based on a salted hash of the password. The actual credential never leaves the client machine. For large-scale deployments, Kafka integrates with Kerberos via the GSS API mechanism. This ties the cluster directly into the organization's enterprise-wide single sign-on system, using ticket-granting servers to verify identities securely. By wrapping a SASL user identity framework inside an encrypted SSL transport tunnel, the cluster achieves a robust, layered defense against unauthorized access. Authentication confirms who a user is. Authorization dictates exactly what that verified user is permitted to do inside the system. Kafka natively manages authorization through access control lists, or ACLs. Take a look at this broker routing table. Even if producer A successfully passes TLS and SASL authentication, it does not have blanket access to the cluster. When it attempts to publish a packet to the restricted finance topic, the broker checks the access control list, sees a lack of clearance, and blocks the request entirely. Administrators define these boundaries using command line tools. They assign specific read, write, or delete variables to specific users for specific topics. Once the ACL is updated with a write permission for producer A, the packet is cleared to flow into the topic. This enforces the cybersecurity principle of least privilege. Every producer and consumer group is granted only the absolute minimum permissions required to perform its specific task. Managing individual ACLs for thousands of clients quickly becomes unsustainable. The operational best practice is to implement role-based access control, or RBAC. Under RBAC, administrators define specific roles, like financial data reader or metrics writer, and attach permissions to the role itself. Users and applications are then assigned to those roles, eliminating ACL bloat and streamlining permission audits. Strict authorization limits the blast radius of a potential breach. If an attacker compromises a valid application credential, they can only access the specific topics assigned to that role, protecting the rest of the cluster's data. We have secured the data in transit and verified the identities accessing it. The final vulnerability lies in the physical storage disks, where the data sits idle on the brokers. Apache Kafka has a noted architectural limitation. It does not natively support data-at-rest encryption out of the box. To protect stationary data, engineering teams at Royal Research integrate Kafka with external storage solutions. This means deploying brokers onto encrypted storage area networks, or utilizing cloud-native block storage volumes that provide transparent disk-level encryption. An alternative approach requires modifying the application layer. Development teams can build encryption directly into the producer applications, so the message payloads are encrypted before they are ever published to the Kafka cluster. Surrounding all of this is the environmental layer of defense, network segmentation. This diagram shows the brokers isolated within a dedicated, highly restricted subnet. By placing the brokers in a physically isolated segment of the network, administrators drastically reduce exposure to external threats. Only approved, routed traffic from specific internal segments can even attempt to reach the broker ports. Network segmentation and at-rest encryption act as fail-safes. If an attacker manages to bypass the application layer defenses entirely, the physical isolation of the network and the ciphered state of the hard drives keep the raw data inaccessible. This completed diagram illustrates the multi-layered secure architecture. The vulnerable, open pathways have been systematically replaced by a hardened, verified ecosystem. Data moves safely through SSL transport tunnels. Every connection is authenticated via SASL mechanisms. Internal actions are strictly governed by RBAC and ACL gatekeepers, and the raw information rests on transparently encrypted storage disks. Security postures degrade if left unattended. Kafka and its underlying dependencies must be patched regularly to close newly discovered vulnerabilities in the cryptographic libraries. Administrators must implement continuous log monitoring, feeding broker access logs into centralized security tools to audit access attempts and detect behavioral anomalies. Finally, secure configuration backups and rigorous disaster recovery testing ensure the cluster can be restored cleanly in the event of a catastrophic failure. Securing enterprise data feeds requires precision and maintenance. By layering authentication, authorization, and physical data protection, you ensure your Kafka deployment remains a resilient and trusted engine for your organization's real-time operations.